The field of solar observation is entering an unprecedented golden age. In the last decade, countries around the world have launched solar observation satellites one after another. There are now more satellites than ever observing the sun from space, with 6 currently in orbit. The footage captured by the satellites is sent here to the Solar and Astrophysics Laboratory in California. The laboratory has been developing solar observation satellites since the 1970s. This is the laboratory's imaging server room. The images captured by 5 of the satellites are collated here and then sent out to researchers around the world. Dr. Ted Tarbell has spent the last 30 years researching the sun using satellite observations.
Today we have SDO, Hinode, Stereo, and SOHO.
As the fixed star closest to the Earth, the sun has always been of particular interest to astronomers. Of the satellites currently observing the sun, the newest is SDO, which was launched in February 2010. The satellite can observe the sun in its entirety in both visible and ultraviolet light. When observed in various types of light, the sun appears in totally different guises. In normal light, the sunspots appear as small dots. But when seen in ultraviolet light, in stark contrast to the quiet, still image, the sun appears as a glowing orb of swirling activity. Sunspots are where the activity on the sun's surface is at the most intense. It follows, therefore, that the more sunspots there are, the more active the sun is. Hinode was launched in 2006. Its onboard telescope boasts images of unprecedented resolution. What do sunspots look like under Hinode's gaze? What looked simply like a dot now looks like a moving, living organism. This sunspot is known among researchers as Nippon, as it resembles the islands of Japan. Thanks to the clarity of Hinode's images, various phenomena have been revealed to be occurring around the sunspots. This sunspot is 20,000 kilometers wide. Flames reaching 10,000 degrees Celsius erupt and flicker around the sunspot. The dark ring that frames the sunspot is called a penumbra. When closely examined, the stripes of the penumbra can be seen to flow alternately in opposite directions. The lighter stripes flow towards the sunspot center, while the darker parts flow out. Professor Saku Tsuneta heads up an observation project that uses Hinode. He spent 11 years developing the satellite. He says he will never forget the first image sent from Hinode.
日の出の撮った画像の鮮明さっていうのは何て言いますか、データを科学者として見るという通常の れを超えてですね、やっぱり美しいとさえ言える感じがいたしますね。
In April 2008, Hinode captured the greatest explosion in the solar system. Between the two black sunspots, small sparks of light start to appear until a band of white light suddenly erupts. This is a massive explosion known as a solar flare. The phenomenal amount of energy it emits is equivalent to 100 million hydrogen bombs. Furthermore, a strange phenomenon was also observed where swirls of gas were sucked into the sunspots. Sunspots do not necessarily stay in the same place. They can appear and disappear and are constantly changing. This footage shows the surface of the sun captured repeatedly over a period of more than 10 years. The lighter glowing patches are the sunspots. When observed over several years, it becomes evident that the number of sunspots varies with time. This is proof that the sun's activity changes in intensity. For a long time, the fluctuations in the number of sunspots, and therefore the level of solar activity, occurred in fixed 11-year cycles. The sun, however, is now facing a change in its patterns of activity.
太陽の周期っていうのは割と規則正しくて、時計のようにっていうとちょっと語弊があるんですけど、11年周期で活動が上がったり下がったりしてたわけですね。日の出衛星が打ち上げられた時、2006年秋っていうのは太陽活動の極小期に近かったと。だから少し待てば太陽活動が上がってくるというふうに思ってたんですが、衛星打ち上げ後しばらくしてどうも変だなというふうに思うようになりました。X 線画像を見てるとずっとのっぺらぼうのままで何も起きない時期が続いていると。これは近代的な観測が始まって以来の異常事態と言ってもいいかなというふうに思います。はい。
Having hitherto marked regular cycles of 11 years, the sun was due for a peak in activity in 2011. However, the number of sunspots is yet to noticeably increase. In short, the sun's regular cycles have started to go awry. And it's believed this sudden change may have a major impact on Earth. The first person to ever record sunspots was Galileo Galilei. These are sunspots sketched by Galileo. In the 400 years since, the number of sunspots has continued to be observed. Looking at the records, there was a period of 70 years when there were no sunspots. This period is known as the Maunder Minimum, named after the man who made the discovery. How did this period of no sunspots and low solar activity affect life on Earth? It's impossible to know at first hand how things were at the time, but clues can be found in an unexpected place. This is Kyoto, the ancient capital of Japan. Dr. Yasuyuki Aono is an associate professor at Osaka Prefecture University. He has come to the Yomei Bunko Library. It is here that he read some ancient texts passed down through the Konoe family of court nobility.
昔の人の日記からですね、桜の満開とかあるいは花見をしたとかそういう記述を探しております。
The timing of when cherry trees bloom is determined by the temperatures at the start of spring. With this in mind, Aono looked for diary entries that would provide clues to the temperatures at the time.
庭先山桜ようやく同じく盛り。植物というのは非常に正直にで、特に桜なんかはもう敏感に気温の条件に左右されますので。
The research showed that in the early 1600s, cherry trees were in full bloom about 100 days after January 1st. But by the late 1600s, the day of full bloom came more than 10 days later than this. Using this data, Aono was able to compute the temperatures at the time. This showed that during the 70-year Maunder minimum period, the average temperatures were nearly 2 degrees lower. During the period of low solar activity and fewer sunspots, it is thought that Kyoto went through a cooling phase. In fact, Japan was not the only place that experienced cooling. The River Thames flows through the center of London. This painting from the late 1600s shows a frozen Thames. During this time, poor crop harvests were recorded across Europe. The Maunder minimum, when sunspots disappeared and solar activity plummeted, was a period of global cooling. The Earth is warmed by the sun's light. When sunspots were scarce and activity levels low, how much weaker was the sun's light? An American solar observation satellite has been making accurate measurements of the levels of light given off by the sun for more than 40 years. These are the results. What is surprising is that whether the sun is at its most active with lots of sunspots, or whether its activity levels and number of sunspots are low, the level of light it emits varies by a mere 0.15%. It is practically constant. But if the levels of light from the sun did not decrease during this period of fewer sunspots, why then did the Earth's temperature drop? The answer lies not in the sun's light, but elsewhere. Big Bear Lake in California, USA. A narrow road stretches out into the lake. A white dome stands at the end of it, as if it's floating on the water. This is Big Bear Solar Observatory, operated by the New Jersey Institute of Technology. The observatory was rebuilt in February 2010. It houses the world's largest solar telescope. Professor Phil Goody is the director of the observatory. He has spent the past 40 years studying the sun.
Good, good.
This is the observatory's state-of-the-art telescope. It stands 8 meters high. It is painted white all over so as not to absorb the sun's heat.
This mirror is the largest aperture mirror for any solar telescope in the world and makes it the most powerful solar telescope.
Collecting the light coming in from the dome window is a 1.5 meter wide reflecting mirror. Compared to artificial satellites, the advantage of ground-based observation is that large telescopes like this can be used. The major disadvantage, however, is the presence of air. The turbulence in the heated-up air causes the images to be blurred. There are two ways in which the observatory combats this problem.
3 kilometers of open water to the west, and so we have nice smooth air coming in, and that enables us to correct our images with adaptive optics all day long.
By placing the telescope on water, which is less likely to warm up than the ground, there is less turbulence in the air around the observatory. The second way to solve the problem can be found in the room where the light gathered by the telescope is analyzed. An observation room lies directly under the telescope. The light from the sun captured by the telescope is guided down from the ceiling. The light passes through several mirrors and lenses into the observation equipment. The mirror in the middle is specially designed to minimize the atmospheric distortion. Amazingly, it can change shape in an instant. A high-speed camera detects turbulence in the air, which prompts the mirror to change shape in order to correct any distortion, producing a pristine image. This special technology is called adaptive optics. Here is how the technology works. A 30,000 kilometer square area of the sun's surface is magnified. It shows hot gas bubbling up from the interior. The image is in focus, but because of the turbulence in the air, it is blurred. This is where the adaptive optics equipment comes into play. At once, a crystal clear image is revealed. The telescope can be employed to observe the sun using a special type of light known as H-alpha. Several curved lines can be seen. This in fact shows the source of the sun's activity. These curved lines may look strangely familiar. They are identical to the magnetic field lines that appear when iron filings are poured over a magnet. The curved lines show that there is magnetism everywhere around the sun.
Those jets are plasma that's excited and sent up and it tracks along magnetic field lines, so you can see an outline of the magnetic field of the sun, and on the smallest scale it's everywhere. So that's a surprise. The sun is truly a magnetic star.
The sun is covered in magnetism. The surface may appear quiet and still, yet it's 100 times more magnetic than the Earth. Where the intensely active sunspots lie, it can be as much as 10,000 times more. The sun is covered all over by distinctive loops of magnetic field lines produced by the strong magnetism. This magnetism is generated in the sun's interior. There is a 400,000 kilometer deep layer under the surface of the sun, where hot gases circulate in convection currents. It is thought that the sun's magnetism is generated by the energy of the moving gases at the bottom of this layer. The sun's magnetism can be seen in its full glory during a total solar eclipse. The sun's atmosphere, called the corona, only appears at the moment the moon obscures the intensely bright sun. Examined closely, a streaky pattern can be seen. These streaks are the magnetic field lines that the Sun, the magnetic star, emits into space. It is this magnetism that causes the various phenomena on the Sun. The flames that flicker on the surface of the Sun are prominences. These prominences are eruptions of gas caused by magnetism. This phenomenon can be recreated using a magnetic toy. When a magnetic top is spun on top of a stand, the magnetism causes the top to float in the air. Similarly, prominences are plasma gases that float up through the power of the Sun's magnetic force. Solar flares are the largest explosive events in our solar system. They are also caused by the Sun's strong magnetic force. Magnetic field lines shoot out from inside the Sun onto the surface. When the lines are pulled together at their base by convection currents, the two sets of lines connect. At this point, the magnetic field lines recombine. The newly reconnected lines contract like an elastic band. They snap back and force gas down onto the surface of the Sun, leading to a violent explosion. The intense activity seen on the Sun is the product of the massive magnetic energy that is constantly generated inside the star. In fact, the Sun's strong magnetic field extends so far that it envelops the whole solar system. This magnetism lies at the root of the various activities seen on the Sun's surface. The Earth, too, has a magnetic field. Its field lines extend neatly from north to south. In the Sun's case, however, the magnetic field lines are arranged in a complex tangle. The Sun's secret lies here. The Sun rotates on its own axis once every 27 days or so. Being made up of gas, its rotational speed can vary. It rotates faster near the equator and more slowly at its poles. This means that the magnetic field lines that run from north to south in its interior are gradually pulled sideways and end up wrapped around the Sun. Field lines vary in density, and where they are lighter, they float up to the surface. When these field lines break through, they form sunspots. Sunspots are areas where the strong magnetic force created inside the Sun shoots out of the surface. What happens then to the strength of the magnetic force when there are changes in the Sun's activity? As previously seen, light levels stay fairly constant, even with changes in number of sunspots and levels of solar activity. Here, the strength of the Sun's magnetic force is added to the graph. The magnetic force varies greatly. Furthermore, the changes correlate perfectly with the levels of solar activity. The Sun's magnetic force fluctuates wildly with the changes in solar activity levels. A hitherto unimagined possibility has emerged that it is in fact this magnetic force that has a major influence on the Earth's changing temperature. In the late 1600s, when sunspots disappeared and solar activity dropped, the Earth experienced global cooling. Why did the Earth's temperature fall when solar activity levels decreased and the Sun's magnetic force weakened? In 1997, a paper written in Denmark caused shockwaves around the world. It claimed that the Sun's magnetic force affects the Earth's clouds. The author of the paper lives in Denmark.
Yes, hello.
Professor Henrik Svensmark is based at the National Space Institute, otherwise known as DTU Space. Since publishing his paper, Svensmark has continued to research the relationship between the Sun and the Earth's climate.
The laboratory. This is what we call our sky experiment. We are testing how clouds are forming, or some of the processes that are important for cloud formation.
Svensmark noticed a strong correlation between cloud cover and something rather unexpected. This graph shows levels of cloud cover as measured by satellites. Svensmark discovered something else that fluctuates in the same way as levels of cloud cover. It was cosmic rays, the radiation that showers down from space. Cosmic rays are a type of radiation generated in outer space when a star reaches the end of its life and explodes. Some of the rays travel across space over a long period of time and reach Earth. Svensmark noticed that when there are more cosmic rays, the Earth's cloud cover increases, and when cosmic rays decrease, cloud cover falls.
That is, it's a big surprise, and the agreement was fairly good, even though it was a short period that we had data. The agreement was very good, but the mere idea that there could be such a connection, I thought was very exciting.
Up until then, no one had ever imagined a relationship between cloud formation and cosmic rays. This idea first occurred to Svensmark when he thought of an experiment he had seen at high school.
Which is what we have here. Of course, the cloud chamber at that time was much smaller, but it's the same principle. It works by through the chamber.
This is a cloud chamber, an apparatus filled with vapor.
There's one there, but it lasts only maybe a second, and then it's gone.
From time to time, white streaks appear. These streaks are the tracks of the cosmic rays that fall onto Earth from space. When cosmic rays pass through the vapor, cloud-like forms appear.
I thought immediately that if cosmic rays are important, it might be clouds. It might be clouds that they are affecting. So that was the basic idea.
Svensmark believes that the cosmic rays that fall from afar cause clouds to form. It is widely known that the Sun's magnetic force affects the levels of galactic cosmic rays. Cosmic rays fly down towards Earth. The Sun's strong magnetic field, however, extends all the way across the solar system. This acts as a barrier, making it difficult for cosmic rays to break through. But when solar activity levels drop, the magnetic shield weakens, allowing more cosmic rays to enter the solar system. The cosmic rays can then reach the Earth's atmosphere. In short, the volume of cosmic rays that reaches Earth is determined by solar activity levels. Here, solar activity levels are added to the earlier graph. It is evident that when solar activity is low and the magnetic shield weakened, more cosmic rays fall on Earth and there is greater cloud coverage.
What is important is the sun's magnetic field, which shields against the cosmic rays. And when this shield changes, it changes the Earth's cloudiness and thereby the temperature of the Earth. So the solar activity and the plasma that comes from the sun, or the magnetic field, is really what controls the climate.
Clouds are not formed by water vapor alone. They can only form with the presence of tiny particles that act as seeds around which water vapor gathers. In this photo taken above the Pacific Ocean, white streaks can be seen. These are clouds created by ships traveling across the ocean. Water vapor gathers around the tiny particles found in the ship's exhaust, forming clouds. Svensmark theorizes that cosmic rays affect the formation of these particles. When cosmic rays reach Earth, they collide with molecules in the air. The molecules then become charged with electricity and are drawn to each other, growing bigger and bigger. This gives rise to the tiny particles necessary in cloud formation. According to this theory, the particles become cloud seeds for water vapor to gather around, and clouds are formed. Svensmark's theory of climate change on Earth can be summarized thus. The Earth is protected by the sun's magnetic field, but when this is weakened, higher levels of cosmic rays can reach Earth. This creates more particles up in the air, giving rise to clouds. As a result, sunlight is blocked and the Earth cools.
What is happening in the space surrounding us is very important, and the solar activity can change the number of particles, which changes the cloudiness on the Earth, which changes the climate. So that is the connection. That it's very surprising, but that is how things look now.
Svensmark's claim that the Earth's climate is influenced by space sparked a heated debate worldwide. His theory is now being verified around the world. The most extensive verification of the theory is being carried out just outside Geneva in Switzerland, at the European Organization for Nuclear Research, known as CERN. Large-scale research, such as studies into the origins of the universe, is being carried out using the world's largest particle accelerator, which is 27 kilometers long. One of the projects being carried out here is the cloud experiment, which investigates the relationship between cosmic rays and clouds. Consisting of an airtight chamber 3 meters in diameter and 4 meters high, it is the only facility in the world which can recreate the conditions of the atmosphere anywhere on Earth. Using this, scientists can test whether cosmic rays really do cause clouds.
So this is the cloud chamber where we recreate the atmosphere and investigate the effect of cosmic rays from the beam on cloud processes.
Dr. Jasper Kirkby uses this chamber to run the cloud experiment. He started the project 3 years ago as a result of Svensmark's research.
Fingers have a lot of
26,000 liters of air can be trapped inside this airtight chamber. The ceiling is fitted with lights that irradiate the same strong ultraviolet light that comes down from the sky. The experiment simulates the composition of the air, the temperatures, humidity, and light levels to recreate the exact same conditions as the atmosphere where clouds are formed. The chamber is then showered with cosmic rays artificially created by the accelerator. The researchers then carefully check for the tiny particles necessary for cloud formation. The results can be seen here. When the chamber is irradiated with artificial cosmic rays from the large-scale accelerator, the chamber quickly begins to fill up with tiny particles. When these particles grow, they form the seeds that give rise to clouds.
We've run for 3 so-called campaigns, and we're finding a very strong effect when the beam goes through the chamber. These particles, these seeds for cloud droplets, or at least the embryonic form, the very small version of them, do form much more abundantly when the beam goes through.
Furthermore, it has been found that when the number of tiny particles increases, the nature of the clouds themselves changes. Research has been carried out using Japan's Earth Simulator supercomputer. Professor Kanya Kusano of Nagoya University studied the effect the number of tiny particles has on cloud formation when the amount of water vapor is fixed. In this simulation, air containing water vapor is warmed up on the ground and rises. The water vapor gathers together up in the air and forms clouds. In time, rain falls from the clouds, and the clouds disappear. The number of tiny particles that form the cloud seeds is then varied. When there are fewer tiny particles, the water vapor that rises does form clouds, but it quickly leads to rainfall and the clouds disperse. With a large number of tiny particles, however, there is hardly any rainfall, and the clouds remain for longer. Kusano has a theory of what causes this difference. The amount of water vapor is kept constant. When there are fewer tiny particles, more water is concentrated on each particle, creating big droplets that fall as rain. With lots of tiny particles, however, each particle attracts less water, creating droplets that are too small and light to fall as rain. The number of tiny particles determines whether the droplets turn into rain or stay as clouds. And this has major repercussions on the amount of light that reaches Earth. When solar activity drops and the sun's magnetic field weakens, more clouds are formed, which may lead to a cooling of the Earth. Will the present lowering of solar activity levels continue, or will it return to previous levels? Researchers are looking to the past for clues to the future. The island of Yakushima, a natural World Heritage Site, offers an answer. Dr. Hiroko Miyahara from the University of Tokyo's Institute for Cosmic Ray Research is investigating trends in solar activity levels from the past 1,000 years. She's here to study the Yakusugi cedar trees, aged 1,000 years or more. A growth ring sample from a fallen Yakusugi tree is carefully extracted. This sample contains a special substance that provides valuable clues to the sun's activity in the past. That substance is carbon. When cosmic rays hit the atmosphere, carbon dioxide containing a special kind of carbon called C14 is produced in varying amounts, depending on the number of cosmic rays. The yakusugi trees absorb this carbon dioxide through photosynthesis. As a result, in the years when the Earth's atmosphere saw a high volume of cosmic rays, the growth rings contain a greater quantity of C14. This means that by measuring the quantity of C14 in each growth ring, the amount of cosmic rays that fell on Earth that year can be ascertained. Miyahara carefully peeled apart each growth ring of the yakusugi and collected around 1,000 years' worth of samples. By looking at the changes in volume of cosmic rays over 1,000 years, she can calculate the solar activity level of each year. She also noticed something interesting before the Maunder minimum. That was the period in the 1600s of low solar activity and global cooling. It has been discovered that immediately prior to this, the sun's cycle was 13 years instead of the usual 11. Furthermore, there have been dips in solar activity levels 3 times in the past 1,000 years, and before each one, the sun's cycle had lengthened. In other words, a pattern emerged where each time the sun's cycle lengthens, a period of several decades of low solar activity follows.
今後長期的に太陽活動がどういうふうになっていくかというのは、実は次の10年間が非常に重要な鍵を握っています。ですので今後数年間非常に太陽から目が離せない状態にあるというふうに考えています。
Nobody even knows what the upcoming solar maximum is going to look like or when it will be. So everything is a surprise. So you need to have as many eyes on the sun as possible.
最新の観測が始まって以来、我々が経験したことがない、太陽活動を今迎えつつあるんではないかというふうに考えています。
The importance of solar observation is greater than ever before. In the U.S., a mission is being planned to send a solar probe directly into the sun's atmosphere. In Japan, too, preparations are underway to launch another solar observation satellite in 2018. At the National Astronomical Observatory of Japan, Professor Tsuneta of the Hinode Project is leading the development of this new satellite.
太陽っていうのは地球の生命とか気候に影響を与える唯一の天体なわけですね。で、太陽の研究によって太陽の活動の将来を予測していくことによって我々のその人類への影響を把握していくという意味でも非常に大事な分野だというふうに思います。
And I think the sun is very likely having a very strong effect on our climate, but we don't understand it scientifically. So I think it's our duty as scientists, all of us, the climate scientists, the solar scientists, satellite physicists, everybody, to really pool their capabilities and understand our star, which is controlling our lives.
The sun is mother of all life on Earth. Scientists around the world are researching what will happen to Earth when the sun's activity falls. What they discover will have important repercussions for all of us here on Earth.